Second example for uniform circular motion, centripetal force, we have a student of weight 667 newtons rides a steadily rotating Ferris wheel. At the highest point, the magnitude of the normal force on the student from the seat is 556 newtons. A, does the student feel light or heavy there? B, what is the magnitude of normal force at the lowest point? And if the wheel speed is doubled, what is the magnitude of normal force at C, the highest, and D, the lowest point? So since it's steadily rotating, that means that we have uniform circular motion, which means that we're going at a constant speed, and therefore our centripetal acceleration will be constant as well. So when we have something like a Ferris wheel, we have a wheel like this, and then we have two different free body diagrams at the bottom and at the top. So both of these free body diagrams look the same, all right? So what I mean by two different is I mean that the acceleration is going to be in a different direction. So obviously the student is sitting on the seat in the Ferris wheel, normal force is up, force of gravity is down. Now, since we're moving in a circle here, we know that this is a centripetal motion and we have a centripetal acceleration that's changing the direction of that velocity. So we know centripetal acceleration always moves towards the center, or is pointed, sorry, towards the center of the circle. So at the top, the centripetal acceleration is downward. At the bottom, the centripetal acceleration is upward, which is totally going to change our normal force because of that direction of centripetal acceleration. So we know that they give us the student's weight, or the force of gravity, is 667 newtons. Now at the top, the normal force is equal to 556 newtons. So remember, normal force is your apparent weight. It's kind of how you feel. Since the normal force is smaller than the force of gravity, that means that for part A, at the top, the student feels lighter because the normal force is less than the force of gravity. Okay. Now that's for part A, and that's all they wanted to know for part A, which makes it easy. Part B says, what is the magnitude of the normal force at the lowest point? Now, in order to find part B, we do have to find the actual centripetal acceleration. All right. And we don't know velocity. So we can't find it from that, but we can find it from the information that's given to us about the highest point. So for part B, first we have to find the centripetal acceleration. All right, because we want to know normal force at bottom. So if I use the information that they're giving me at the top to find centripetal acceleration, again, at the top, I know normal force is up, force of gravity is down, and then the acceleration is downward. So this is at top. Now, if I use Newton's second law here, I get net force is equal to mass times acceleration. Here I'm solving for acceleration. And I know, again, this is a centripetal acceleration. Now, I'm going to call downwards positive because that's the direction of my acceleration, and I get force of gravity minus the normal force is equal to mass times acceleration. Now, I know what force of gravity is. I know what normal force is at the top. I can find mass because I know force of gravity is equal to mass times acceleration of gravity. So that means that mass will be force of gravity divided by acceleration of gravity. So that's 667 divided by 9.8, which is 68.06. So mass equals 68.06 kilograms. So now I can plug my numbers in. I get 667 newtons minus the normal force at the top, which was 556 newtons, equals the mass of the student, which was 68.06 kilograms, times acceleration. So 667 minus 556 divided by 68.06, we get an acceleration of 1.63 meters per second squared. All right, so now that we know the acceleration at the top, we know it's going to be the same acceleration at the bottom, but of course it's going to be a different direction. So at the bottom, we have the same free body diagram, But again, the acceleration direction is different. So now when we use Newton's second law, that normal force is going to be the positive force, and our force of gravity is the negative force. So again, we know acceleration. Here we're solving for normal force. So we get normal force is equal to ma plus fg. Normal force is then going to be the mass, which was 68.06, times acceleration, which we just found to be 1.63 meters per second squared, plus the force of gravity, which was 667 newtons. I'm sorry, I dropped my units. I was running out of room. So we get 68.06 times 1.63, and then I'm adding 667 to that, and we get that the normal force on the bottom is 777.94 newtons. So the student feels heavier at the bottom because the normal force is larger than that force of gravity. So that's part B. Now for part C, we want to know if the wheel speed is doubled, what is the magnitude of the normal force at the highest and lowest points? So we want to see what happens to acceleration when we double the speed. So for part C, we know acceleration is a centripetal acceleration, which means that's v squared over r. Now, if we double v, that means we're quadrupling a. Does everyone see that? So you're squaring that velocity. So doubling v quadruples. How do you spell that? Is that how you spell quadruples? It quadruples acceleration. So that means that my new acceleration is going to be 4. I say 4, but I write 6. 4 times that 1.63 meters per second squared. And we end up getting 6.52 for that. So that's our new acceleration. And now we just want to find the normal force for the top and for the bottom when we have an acceleration of 6.52. So at top, again, remember downwards is the acceleration at the top. So we get force of gravity minus the normal force is equal to mass times acceleration. Solving for normal force here, we get normal force is equal to force of gravity minus mass times acceleration. I just added normal force to both sides, subtracted mass times acceleration from both sides, and we get that the normal force is equal to the force of gravity, which was 667 newtons, minus the mass 68.0, what was that? 68.06 kilograms times the new acceleration, which is 6.52 meters per second squared. And so at the top, the normal force will be equal to 223.25. And then same thing for the bottom. At the bottom, remember acceleration is up at the bottom, which means the normal force is positive, minus the force of gravity equals mass times acceleration. So here we get normal force is equal to force of gravity plus mass times acceleration. So we get 667 newtons plus 68.06 kilograms times 6.52 meters per second squared plus 68.06 times 6.52. And we get 1,110.75 newtons. So notice how much bigger the normal force is at the bottom and smaller the normal force is at the top when we increase our velocity. So that difference in the force of gravity and the normal force, that difference between the two are bigger when we're increasing velocity, increasing the centripetal acceleration.